The blob problem. We have a region located in the xy coordinate plane. It is formed by two functions, f of x and g of x. The region is bound by the y-axis, the function f of x, the function g of x, and the point of intersection of the two functions, point B. The region is the base of a three-dimensional solid. Our objective is to find the volume of the solid. In order to do so, we will divide our solid into cross-sections, find the area of one cross-section, use a Riemann sum approximation to find the volume of the cross-section, and finally use that volume in calculus to find the volume of the original solid. If the solid is partitioned along the x-axis, its cross-sections are equilateral triangles. This is what a cross-section looks like. If drawn on paper, this is what a cross-section would look like. The base of the triangle is formed by subtracting the two functions top minus bottom, or f of x minus g of x. The next step is to find the height of the cross-section. We divide its base in half to form a 30, 60, 90 triangle, whose sides length have the ratio 1 to root 3 to 2. The horizontal leg of the triangle is half the base of the cross-section, f of x minus g of x over 2. The vertical leg is found by multiplying the length of the horizontal leg by root 3 to get root 3 times the quantity f of x minus g of x over 2. The hypotenuse is found by multiplying the horizontal leg by 2 to get f of x minus g of x. Once we find the legs of the triangle, we know that the height of the cross-section is equivalent to the vertical leg of the 30, 60, 90 triangle, which is root 3 times the quantity f of x minus g of x over 2. Now to find the area of the face of the cross-section, we use the equation for the area of a triangle. Area equals 1/2 the base times the height. When we substitute the values we previously found into that equation, we formed a new equation, 1/2 times the quantity f of x minus g of x times the quantity root 3 over 2 times f of x minus g of x. In order to simplify the equation, we multiply it out, resulting in the equation area equals root 3 over 4 times the quantity f of x minus g of x squared. The root 3 over 4 comes from multiplying 1/2 times root 3 over 2. F of x minus g of x squared comes from multiplying the quantity f of x minus g of x times itself. Now we can use a Riemann sum approximation and calculus to find the volume of a cross-section and then the volume of the whole solid. We can call our cross-section the K slab. We then take an arbitrary point in the slab, calling it xk star. That is the point from which the height of the slab was measured. Therefore, f of x minus g of x becomes f of xk star minus g of xk star. We now have yet another new equation for the area of our cross-section, or the K slab. Area equals root 3 over 4 times the quantity f of xk star minus g of xk star squared. Using that area equation, we can find the volume of the slab. We multiply the area by the slab's depth, or delta xk. We use a Riemann sum approximation to find the volume of the whole original solid. The total volume equals the sum from k equals 1 to n of root 3 over 4 times f of xk star minus g of xk star squared delta xk. This adds up the volumes of all the cross-sections that form our solid. However, this is just a general approximation of the volume. The more slabs, that make up the solid, the smaller they are, and the more accurate our volume approximation will become. In order to produce that approximation, we use calculus and take the limit of our Riemann sum as n approaches infinity. This produces the integral root 3 over 4 times the quantity f of x minus g of x squared from the point A to point B. Now that we have this integral, the volume of any solid with the equilateral triangle cross-section can be found by integrating the function root 3 over 4 times f of x minus g of x squared along the x-axis from point A to point B.